Recording. Okay, great. It's recording now. So in this reaction here, what we are going to do is going to figure out what the rate of this reaction is. And I haven't done it before, but I think I should be able to do it. So the rate of the reaction, I'm going to put R of reaction, meaning for this reaction here should be on this form. However, the rate of the reaction is going to be the rate of the slow step. So you have to imagine that this is a production line. So you have a step 1 first and then step 2. Whichever is slower is really going to become the bottleneck for the reaction. So it's going to slow it down to the rate that the reaction can go. So if step 2 is the slowest, that means that it's going to bottleneck and the reaction is going to go at the rate of the slowest step, which is this one here, R2. So the rate of the reaction is equal to R2, and R2 is equal to K2 concentration of NO3. But this is not the way that it should be expressed. It should be expressed in terms of concentration of NO and concentration of O2 all the time. You can never express a chemical at the rate of a reaction in concentration of products or concentration of intermediates or concentration of catalysts. It has to be on the concentration of the reactants. So let's think about step 1 now. So if step 2 is the bottleneck, means that reaction step 1 is going faster and is going to produce NO3, and the NO3 is going to be produced more and more and more, and the concentration is going to increase until the concentration is so high that the NO3 is going to start going backwards as well, react backwards. Remember that this reaction is at equilibrium. So that means it can go one way or the other. When you break, you propose a mechanism, every step of the mechanism is potentially reversible. In this case, then the NO3 is going to start going backwards and enough that it's going to become significant. So let's look at the rate 1 here. And I'm going to rewrite that equation, K1, concentration of NO to the power of 1, concentration of O2 to the power of 1. Now, for the rate going backwards, meaning from NO3 this way to NO and O2, we can say that the rate is going to be, I'm going to call it rate to the -1, meaning backwards. And this is going to have a different constant, which is going to be K to the -1, concentration of NO3. So because if it's going backwards, then the NO3 is the reactant and NO and O2 is the product. So for R-1, for the reaction, the reverse of step 1, the reactant is NO3, and so that's what I'm expressing as a form, as in the form that I'm doing. I'm saying this is the K-1, which is not equal to the K1, and it's not the inverse. It has its own value, and it's going to produce the NO and the O2. So now, if this is an equilibrium, eventually what is going to happen is the NO and the O2 are going to form NO3, and the NO3 is going to be trying to go through step 2, but not all of it will go through. So again, the NO and the O2 keep reacting and forming NO3 until there's enough that is enough NO3 that not only the NO3 is going through step 2, but is going through step -1, meaning going backwards on step 1. And so this is the rate going backwards. This is forwards. And this is backwards. And eventually they will reach equilibrium. So if they reach equilibrium, at equilibrium means that the reaction going forward, R1 is equal to R-1, meaning that it's going to reach what is called a steady state. That means that reaction, the NO3 is going to build up to a point where the reaction going backwards is as fast as the reaction going forwards. And so the reaction going backwards, remember, is going to be proportional to the concentration of NO3. If you look here, R minus 1 is a constant times the concentration of NO3. So it's going to build up, NO3 is going to build up until this happens. The equilibrium will be arrived. So let's write then this, R1 is K1 concentration of NO, concentration of O2, and that's also equal to R minus 1, or the rate going backwards, which is K minus 1 concentration of NO3. So by recalling the equilibrium, what I'm doing is generating an equation now for NO3, concentration of NO3, based on the concentration of NO and CO2, which are the reactants. Which means that now I can solve for concentration of NO3, which I want to get rid of. So this will be like a substitution reaction. When you have two simultaneous equations and you substitute one term into the other, that's exactly what we're going to do. So when I'm going to solve for concentration of NO3 from this equation here, I'm going to take that equation and solve for NO3. So concentration of NO3 is going to be equal to K1, and I'm going to send this divided to the other side, or divide each side by, by K to the minus 1. So I have K to the minus 1, concentration of NO, concentration of O2. And now I will substitute, let me get a different color now, let's get a green one. I'm going to substitute this expression here. I'm going to put it into here. Okay, so we can say that the rate of the reaction now is going to be equal to K2 times NO3, but instead of NO3, I'm going to write K1 divided by K minus 1, concentration of NO, concentration of O2. And then simplifying this, I'm going to say this is K prime, concentration of NO, concentration of O2, where K prime, is equal to K1 times K2 divided by K minus 1. So now I have an expression of the rate for this reaction that, let's make it pink, is going to be of the right form, meaning it's going to look like we said it should look, this one here. R is K, concentration of NO to the power of something, concentration of O2 to the power of something. So rate of the reaction is K, concentration of NO to the power of 1, concentration of O2 to the power of 1. So this is how the rate of the reaction should be expressed. And this is something you need to do. So again, you need to look at, if you have forgotten about simultaneous equations, you have two equations and you solve for one term on one equation and then you substitute in the other, so that term disappeared. Why? In this case, we're doing it with NO3 because NO3 shouldn't be in the rate of the reaction expression, this pink one here. And so we need to get rid of NO3. Here, this is not the proper reaction, the way of expressing the reaction rate for this reaction. So I needed to get rid of NO3. And so I found a different equation by proposing an equilibrium between these two, going backward and forward in the previous reaction. So usually you have to claim the equilibrium in the previous reaction. If there will be a step 3, there wouldn't be an equilibrium there. The equilibrium happens on the back of the bottleneck, meaning on the previous steps of the slower step of the mechanism that has been proposed. Okay, questions, please. Okay, so let's see if we can get back to, so let's see where we go. That's the NO3. This is the, they call it forward and reverse rather than 1 and -1. That's the same thing that we did already. And now we're going to get to another reaction, which is the reaction of NO2. I know that looks similar. I have to look twice to be able to say, this is a different reaction. Yes, because now we are reacting NO2 with carbon monoxide. Carbon monoxide and NO2 are exhaust from our cars, and they can undergo this reaction. Actually, this kind of gets rid of the carbon monoxide, and which is good because the carbon monoxide is toxic, and so is the NO. But at least these two are toxic. The two reactants are toxic. This one is not that bad, so this is okay. So at least we have reduced going from 2 toxics to 1 toxic. Okay, so this is the proposed mechanism. It says to notice that when you sum up, so let's go on again. Here's the step 1, and here's step 2. So you have rate 1, rate 2. Notice that we can write the rates of the reaction by looking at the coefficients only when there is a mechanism, and these are elementary steps. So, so if your problem that you are solving doesn't say that it's an elementary step or a step in the mechanism, only in those cases when it says that it's an elementary step or a step in the mechanism, you can actually take the coefficients and make them the exponents. Like this 2 becomes square. These are 1 and 1, and therefore these are 1 and 1 exponents for the rate 2. The other thing that I want to bring your attention is you can sum them up. So in this case, the NO3, again, this NO3 looks like it's an intermediate of the reaction. How do we know it's an intermediate? Because in the first step, it forms, is the product, and in the second step is a reactant, and it disappears. So those cancel out, and there is an NO2 being formed here, and there's an NO2 in the products. There's 2 NO2s in the reactants. So I can cancel out one of these NO2s with one of these 2. And so making this coefficient 1. I don't see anything else that is common. So now I can add them up. So I have 1 NO2 gas. I have 1 CO in the reactants. This NO is in the products. So let me see if I can get a different color. And so this is the NO goes in here, and this is the CO here. And then you have the reactant. So let me write a line here. That's where the equal signs are. So on the product side, I have NO, and I have CO2. So this is the overall reaction. This should match this reaction here. Now, notice that here they're telling us the rate determinant step is step 1. So if the rate determinant step is step 1, that means the rate of the reaction is going to be the rate 1. And the rate 1 is K1, concentration of NO2 squared. And we don't need to do what we did with the previous equation because NO2 happens to be the reactant, and if it's the reactant, it's okay. So in this reaction, this is the rate law. It's second order on NO2. Notice that it's second order in NO2, although there's no 2 here, right? There's a 1. This is a coefficient of 1. So when you look at the overall reaction, you never will take a coefficient and make it an exponent. Only when you're talking about mechanisms and you're talking about the elementary steps of a reaction. Okay, I like that. I hope that sinks in for you. And here we have a practice exercise. It says for the reaction of NO2 and ozone, yet another reaction of NO2, but this time with ozone. So as you can see, NO2 in the atmosphere is fairly reactive. It's fairly reactive with a lot of things, with plants and animals as well. And so in this reaction, we have the reaction of NO2 with ozone, which is actually a radical compound. Radicals are compounds that have unpaired electrons and therefore are very reactive. Okay. They say that they have determined the rate law to be this. So the rate law for this is going to be, let me write it again here, because it's kind of lost there, right? Is K concentration of NO2, concentration of ozone. So this is not bad. When you determine the rate law, there are a lot of laboratory techniques that we can use to determine the rate law. So that's the easiest. So when people are studying a mechanism first, they want to find out what the rate law is experimentally. You're going to go into the lab as a freshman chemist, you're going to get the rate law for a chemical reaction as well. So that's not that difficult. So once you have the rate law, you can propose a mechanism, and the proposed mechanism is this one. When you get a proposed mechanism, you have to make sure that they add up to the overall reaction, this one here. So let's see if they do. So I can see that NO2 is a reactant here, but there's two NO2, there's one NO2 here, but there's another NO2 in this. So this is the equal sign there. There's the boundary between reactants and products. So we have two NO2. And so, yeah, that check marks there. And an ozone, there shouldn't be an NO3. And I can see that the NO3, this NO3 is going to cancel out with NO3. And the product should be N2O5. Yeah, it checks out. And O2, one of each. So, yep, it works. So this mechanism is consistent with the observed rate law. Let me take a little bit of out here. Too much writing. Okay. So it says to identify the rate determining step in the proposed two-step mechanism. So we need to actually write the rates of the reaction for each of those reactions and see how they look like. And I think I want to move to my notes. So let's go in here. I think I have this one here. Yeah, we had that. Yep. So we can write the rate law for this one. So we can say a rate of 1. I'm in pink, that's okay. Is going to be K1, concentration of NO, 2, concentration of ozone to the power of 1. I can do that because these are steps. This is the mechanism. There's elementary steps. And therefore, I can take from these steps the coefficients to make the exponents. For rate 2, or the rate of the second step is going to be K2, concentration of NO3, and concentration of NO2. So those are it. Now I'm going to compare these rates with the overall rate. The experimentally determined rate law is this one here, K concentration of NO2O3, and I can see that this is exactly this one here. So that means that rate 1 is the rate determining step. And that is going to determine how fast the reaction. In this case, I can see that the equation matches, and this is the first. So there are two steps, the first step. So the first step is the one that is going to be the slowest of those two steps. Once it happens, then the NO3 reacts quickly with another molecule of NO2 to form N2O5. So that's it. So I have determined which is the rate determining step. So the rate determining step is step 1. And this is consistent with the observed rate law. So these two equations here correspond to each other. And therefore, that is the correct answer. Not a very difficult question, really. Okay, so let's get back to the presentation. Okay. Yeah, I cannot advance. So let me leave and come back again. See if that's it. Yeah. No. Yes. So let me close it. Yeah, let's discard those. Okay. So now we should be able to get into this one. Okay. So let's go from here. So now solve step 1, step 2. Oh, this is the solution. Yeah. So they did have this one and this one. These are the two equations that we wrote in my notes. And step 1 matches the experimental row, the experimentally determined rate law, and therefore this is the RDS, rate determining step. Okay. Oh, let's look at the molecularities. The molecularity is another concept that you should know. Molecularity of this reaction is step 1. Step 1 and step 2, molecularity. So we're creating a table here. Oops. So the molecularity for step 1 is 2. Why? Because there's 1 and 2 molecules. And here there's 1 and 2 molecules. So it's 2. Both of them are 2. Now, if this one will be 2, then it'll be 2 and 1 will be 3. If that be the case. So then it will be, but that's not the case. It's 2. Because this doesn't exist. Okay, so the molecularity of the rate determining step is 2, and it matches the rate law, which it says that is first order on each of them. So the overall, here's the rate law, is first order in NO2, first order in ozone. The rate law is second order overall. Okay, great. So let's talk about the last thing about we need to talk is catalysis. So I'm going to break the recording right now into smaller segments so we can start with catalysis.